EX by 4 pi T. You'll see what that will make. This is also a constant, but that's very unique about nuclei in question. If it's a proton, there is a certain G value. If it's a carbon-13 nucleus, for a certain G value. And that is basically the most clinching thing when it comes to using it for chemistry. We will see that later. But the point is, neglecting what these guys are telling you, they're essentially constants. You know that this and this are actually related. The greater the magnetic field that you have applied, the greater will be the splitting between these two levels. And you want to get as much splitting as possible for a variety of reasons. So give me one simple reason as to why you want a big splitting in the first place. Let's go back to our fundamentals. I have three situations, and I gave you 100 molecules, and I said the temperature is 300 K. Where would you find the biggest disparity in population? Here, right? If I had this, what would that mean? You probably have 49 here and 51 here. Energy difference is so small that if you actually worked out your Boltzmann population for such a small energy difference and at this temperature, you'll probably find that you had maybe 49 molecules over here and maybe 51 molecules over here. Your 100 would probably partition themselves out as 49 and 51. What happens here? Maybe it's 40 and 60. Better. Here, maybe it's 20 and 80. Even better. And what about this fellow? Maybe it's 5 and 95. So you can see that as the spacing gets bigger and bigger, or the energy differences become larger and larger, if you had a certain total population, how will they partition out? They will partition out in such a way that you have the greatest disparity and the greatest difference in population. When this difference is the largest, the difference is smallest, what happens? Very close to each other. And when there is no difference, what happens? 50-50. If there is no difference, you basically have equal population in both states. So if I give you 100 nuclei and ask you what's the population in this and what's the population in this, in the absence of a field, what would that mean? 50-50. You don't have to even go about anything. It's 50-50. But then if I apply a field, I'm splitting them. And now if I ask you what is the population difference or what is the differential between these two states, what's the first thing you will ask me? Tell me the energy difference. I'm assuming the temperature is 300 K, which is room temperature. The first thing you will ask me is, tell me the energy difference, and I will tell you what the population differential is going to be. But then to know energy difference, what should you know? The field. So in essence, you're not going to ask me, don't give me the energy difference, just give me the field. I will calculate the energy difference, and once I know the energy difference, I will calculate the population and tell you how much population differential I have between these two things. And if I want to have the largest differential, what should I really do? Apply a strong field. The strong field that I apply can actually split things quite large. And we will look at numbers very soon, maybe in the next class. We will look at numbers to see it's really hard. You already know what the energy level spacing for rotations are, right? 1, 2 wave numbers. And we were already complaining it's not big, it's too small and all that. Now you see it is worse. It's even smaller. When we got to vibration, what did we say? Oh, things are getting better. This 1000 wave numbers. And the moment we said this 1000 wave numbers, what is the population? Ground state had 95%, upper state had 55%. Go to electronics, what's the difference? Differential. 40,000 wave numbers. So out of 100 molecules, what happened? Oh, almost all 100 were in the ground state, and nothing was in the excited state. Here, the energy difference is much smaller. Even in the presence of very strong field, it's much less than what you have for rotations. But the stronger the field that you apply, the better it is. And when you have a reasonably large spacing, then you have a reasonably large population differential. So why do you want large fields? You want large fields so that I can establish a reasonably big differential in population between the ground state and the excited state. What's the ground state in this case? The ground state is plus half state. And you can say the plus half state is the one in which the nuclei is oriented this way. This is plus half. This is minus half. And this is my field range. So the nuclei, the field is this way. The nuclei is actually wanting to spin this way. projection all the time, plus half. If it is this way, it's plus half. If it is this way, it's still plus half. This is plus half. So while this angular momentum vector is rotating all the time and changing its value, it's a vector, and changing its value, what is not changing its value? The projection. And quantum mechanics people have this very nice language. They say this is not a good quantum number, whereas the projection is a good quantum number. They use that language. And all they're saying is that while this is constantly changing, the projection is not changing. That's all it means. So when this is doing this, what is the projection? Plus half. When it is doing this, what's the projection? It's minus half. If I apply the field, what happens? This becomes favored. And this becomes not so favored. So which means that earlier without the field, there were 50 guys doing this and 50 guys doing this. Now suddenly if I apply the field, you'll find that there are 60 guys doing this and 40 people doing this. Population differential. Why? Because the plus half state is more stable than the minus half state. And these protons, for that matter, anything in nature, wants to take the lower energy state. But not all of them can take it. Because the Boltzmann population distribution will tell you how many of you can go here and how many of you have to go up there. E power minus delta E over KT. Of course, there are two j's of one term which is in the front. But that exponential term is the whole crux of the Boltzmann distribution, which tells you how much can go up and how much can go down. The spacing is large, there is a big difference. Spacing is small, very small difference. Spacing is zero, equally populated. So we get that point clear. So we are applying magnetic field to create a population difference, create an energy difference, and consequently a population difference. And the bigger the energy difference that we provide, the bigger is going to be the population differential that we are going to create. So you can ask me, why the hell are you still talking about for so long about a population differential? Why do I need to have such a big difference in population? What's the problem? If I have, 49 and 51, why do you want 40, 60 or 80, 20? Why do you think we need that? Why do you think we need that big population differential in any experiment? And for that, you need to look at something that you probably know, but we must learn to apply it over here. If I have two states here, if I have, let us say, 5 molecules and nothing upstairs, 5 molecules in the ground state, nothing upstairs. I bring in light, and let's say the light has the right frequency to take the molecule from here to here. In other words, the light is resonant with that energy spacing. What would happen now? Well, maybe one of these guys will absorb, and you go up, and the photon is gone. It's absorbed because it's absorbed and taken up, the photon is lost. Molecule is updated. Now let's say I come into the second photon. What do you think the second photon will do? Well, it can cause the second guy to go up, and I'm assuming that this will have a large lifetime. So it doesn't come down easily, it just goes up there and stays for a while. Let's assume for a very large lifetime. So the second photon comes here, and what's the possible scenario it can enact at this point in time? The second molecule can absorb, and that can go up. So now you have not 5 and 0, not 4 and 1, you probably will have 3 and 2. Progressively you are pumping molecules from the ground state to the excited state. But there's one little thing we forgot. There's one other act the molecule can do, and what is that? As the photon comes in, I don't know whether you learned this in physics, this guy can actually be driven from this state down here by this photon. And what do you call that process? Stimulated emission. The molecule can emit light of its own and jump down, and we call that as spontaneous emission. But the molecule can also be driven to go from here to here by this photon that's coming in, and we call that as stimulated emission. The laser in fact works on that principle of stimulated emission. So this molecule sits up there. If there were no photon ever, it will live its lifetime and then jump down, giving you an emission photon. And what is that process we call? It's an emission process, which you have been doing since morning, fluorescence spectroscopy. You excite the molecule, then you wait for the molecule to jump back, and you're looking at fluorescence. However, before the guy jumps back, if I come in with another photon, that photon can actually do one of two things. And what are they? It can drive one guy from here to here, or it can drive this guy back downwards. It can either cause absorption absorption, or it can cause stimulated emission. Both are possible. But now tell me, which is more possible? Now that you know the second possibility exists, wherein the molecule can actually jump from the upper state to the down state, driven by the photon to do so. It is not jumping spontaneously. It is not jumping of its own free will. It is actually being driven to come down by the photon. It's actually a driven process. It's not a spontaneous process. This is a stimulated process. Absorption is a stimulated process. Molecules of their own accord just don't jump up. You have to give life. You have to give heat. You have to give a discharge. Then they jump up. Now what I am telling you is that same non-spontaneous process can also occur in emission. Molecule sits there, waiting to come down. But before it has lived its lifetime, if there is another photon that comes in, it is quite likely that that molecule can be driven to the ground state by this photon, and we call that as stimulated emission. The very heart of a laser. So every time you see a laser pointer going, you know that inside there is stimulated emission going on all the time. Of course, how can you get stimulated emission to be a dominant process? That's a different story altogether. But I can do it. So now I want you to answer me or ask this question. First photon went up. So in the very first scenario, there was no question of stimulated emission. I didn't have a molecule up there in the first place. Now, I'm here. What do you think will happen when the photon comes? This fellow can go there, or this fellow can come down. Which do you think is more probable? Which one? How many of you think that this is more probable? How many of you think that this is more probable? How many of you think that the molecules won't even care about it? Because molecules will care about it. But the third answer is also right. When the third photon comes, it's quite possible that no absorption takes place, no emission takes place, the molecule is it all depends on cross sections, right? There's a certain probability of not happening, nothing happening. And that's probably what I think you're trying to tell me. I will assume that you're trying to tell me. Very profound answer, and I will attribute that profoundness to your silence. Okay. So now, those of you who said that the downward process is more probable, why do you think that? Yeah, I'm sure you have a reason. Everybody wants to lose energy and get down as quickly as possible. So when there is somebody helping you to do it, why not you do it? But then why do the people who said this is more probable? Why? There are four, at least one, See, you have four guys sitting downstairs wanting to go up with this photon. There's one guy sitting up there wanting to come down. And there's one photon to go around. So it's basically a fight between 4 against 1. And on sheer probability, who will win? The flow will win. So therefore, this is more likely to happen. I'm not excluding the possibility of this happening. All I'm saying is, this is more likely to happen because there is a 4:1 probability that this fellow will win. Let me make it 6. I need an even number to complete the argument. Next photon comes in. What do you think will happen now? 4 and 2. There is a probability of this coming. It is actually better than the last time. Last time I had 1, now I have 2. The probability has got better. But there is still a probability working against it. 3 and 3. Therefore, this goes up. Now there is 3 and 3. Now what do you think will happen when the next photon comes? There is an equal probability of this happening both ways. And therefore, if you look at the average behavior of the system will just not absorb the that photon will come through straight. Because there is as much probability of one photon going up as there is a probability of one photon coming down. You then say the system has actually saturated. System has saturated. And therefore, this photon will actually not be absorbed. If you take some substances like even fluorescein, which is very strongly absorbing, and you keep on absorbing light, shining light on it, what do you think will initially happen? Initially, you will find that the absorption increases, and after a while, you will see the absorption doesn't change. Why doesn't it change? Average saturation. Half the molecules are in the ground state, half the molecules are in the excited state. There is equal probability of things happening both ways, and therefore the system actually behaves as if there is no light falling on it, because there are as many molecules coming down as there are molecules going up. This is exactly what happens in an equilibrium reaction. A plus B giving you C plus D. You all know that, right? What happens there initially? By an equilibrium reaction, I start with A plus B. I put it into the beaker. What will happen initially? A plus B will give me C and D. To begin with, that will happen. But then what will C and D do? They won't keep quiet because they have to get back. Just like this fellow wants to get back. But initially, that's not going to happen. Initially, the probability is this will happen because I have a large concentration of this and a very small concentration of this, and we know the rate depends on the concentration. So initially, this is going to happen. And after a while, what happens? When this fellow builds up, just like this fellow was building up, what happens over here? The reverse will start to tell or will start to make an influence, make an impact on the whole scenario. And what happens at equilibrium? At equilibrium, it is not an A plus B and C plus D called truths and say now we will just keep quiet doing nothing. No. There are as many A plus B's going to C plus D as there are C plus D's going back to A plus B. And we keep using this word that's called a state of dynamic equilibrium. It looks nothing is happening, but there's a whole lot of things actually happening. It's not manifested to us because the two rates are equal. Exactly the same thing happens over here. When these two become equal, it is not the system is not going anything. There are as many molecules absorbing a photon and going up as there are molecules jumping from giving a photon back. And therefore you will see for every 3 photons absorbed, 3 photons coming out, see nothing seems to be happening. You then say the system has saturated. Just like the system had saturated in this process at equilibrium. Dynamic equilibrium. Dynamic equilibrium. Now we are getting to the point. So if I really want to have a good absorption